Okay, document, document. Okay, are you able to see the document? Hello, Viramani, are
Yes,
you
sir.
able? Are you able to see the
Good
PDF?
Yes, sir. Yes,
good
sir.
afternoon, sir.
Good afternoon. Yeah, now you switch off the mic and you just focus on the document that I'm sharing with you. So please switch off your mics. I'm recording the class. So in today's class, we are going to learn about the dimensions of the induction machine. See, I have already yesterday we discussed about the output equation of the induction machine, wherein we have proved the output equation of an induction machine is equal to how much is equal to your output equation is equal to C d square L n S. So what is your C? C is what? C is the output coefficient which is constant and it depends upon your these values which you can see over here. I'm just this is my C naught 1.11 into pi square BAV is your specific magnetic loading, AC is your specific electrical loading into kilowatt in 10 power minus 3 d square LNS. So this whole portion happens to be C naught, and this portion d square, which d square L is the volume of the conductor. D square unit would be in meter square because it's the diameter square, and this ns is the synchronous speed of the machine, which yesterday also we have seen, and also I have shared with you a YouTube video. Today I'm going to go into some how to design the stator and how to implement that design, and we will be solving one problem so that would be very clear for you. So basically, before going to this design of induction machines, let's brush up. See, this is my power triangle. So in my power triangle, this portion is my hypotenuse. This is my complex power that is given by kVA. This is my power factor angle phi, and this is my kVAR. Now, if I want to write cos phi here, so it would be base by hypotenuse. So base is kW, so it would be kW by kVA. So in other terms, kW by kVA is equal to cos phi, or we can directly write your kW is equal to kVA into cos phi. So one more important thing to notice is that your input kVA, see, your efficiency is how much. Efficiency is your output by input. Output by input is your efficiency. So your input kVA would be your output kVA divided by efficiency. So here also you can write, see, input kVA, you can write from this formula. Input kVA is how much? Input kVA is equal to kW divided by C, kW divided by efficiency into cos phi. If you relate these three equations, you will arrive at this. Input kVA is equal to kW into efficiency into cos phi. This is elementary basics. This is not big thing over here. Suppose your power is not expressed in kilowatts. Now your power is expressed in horsepower. So what we are going to do is that if it is expressed like this, so you will multiply it with 0.746 into HP would give you the value in kilowatt divided by efficiency into cos phi. Now, whenever we are calculating these terms from output equation, we need to separate these terms d square L and S. So here this C naught is called as the output coefficient of AC machines. So your power output power would be C naught d square L N S kVA. Now volume of the machine is d square L. So you can write d square L is equal to input kVA, that is your input kVA here, by a constant term. Constant term would remain what? One constant term would be your C naught, and ns will remain constant because ns is what? Is the synchronous speed. It is dependent on the number of poles. It's 2f by p. Frequency will not change. It will always remain 50 hertz, and the number of poles which you are connecting, it will also not change. Hence it will remain constant. See, similarly in C naught you are seeing ampere conductors. This will not change. Average magnetic flux density, it will not change. Hence it's given volume of the machine is d square L is equal to input kVA by constant. And this volume, obviously the dimension of d would be in meter square and length in meter, so meter in meter square into meter would be meter cube. Now from this particular thing here also, see, I have mentioned efficiency is input by output, then output is equal to input by efficiency. So what we are interested is, this was our output equation. We are interested in how to calculate particular terminologies. Like for example, here you can see ratio of core length to core pitch. Your core pitch would, z is this, length would remain as length. The z is given by the circumference of your pole pitch divided by the number of poles. That is your, how many, see, d is your 2r, so this is circumference 2 pi r. Instead of writing 2 pi r, we are writing it pi d divided by p. So there, yesterday's class also I have shared certain things. You have your,
Yes,
yeah, yeah, tell me, any doubt? Huh? Hello?
many are to join, sir.
Yes, 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 yeah, tell me. So, are you able?
Still many are to join.
Huh? What? No, no. I have already given a YouTube lecture also on that. They can, if certain people are joining late, no problem. They can see that in my YouTube session also. It is also similar to it. I have uploaded on my that channel. You can see that, and those people who have joined can follow, because we have to start the class. Okay. So see, if your L by Z ratio is not given in the problem, then for good overall design, what we do is that L by Z usually we take it as 1. Now overall, good overall design means your everything, your dimensions, your induction motor length, volume, and the cost of material, including your power factor, minimum cost, everything should be optimum. For that, we take L by Z value as 1. Now for example, we need a good power for best power factor. In that case, we are taking Z is equal to under root of 0.18 L. For minimum cost, we are taking L by Z is equal to 1.5, between 1.5 to 2. Now the see, now there is also some velocity, because the machine is moving with some velocity. So the distance covered by the machine per unit time is known as the peripheral speed, or the velocity of the machine. So every machine you are seeing in your machines lab also, you have seen when you go switch on the lab induction motor, that shaft starts to rotate and it has some RPM, some velocity. So that velocity depends upon your diameter of the machine and the synchronous speed in rotation per second. See, synchronous speed, that N 120 F by P, that is in rotation per minute. But here we are taking it in rotation per second. So in that case, your NS would be equal to not 120 F by P, but how much it would be equal to? Yesterday's class we have given it. Your small NS is capital NS by 60. So it would be almost your 2 F by P. Now here the velocity is given by, again, velocity would depend upon the circumference and this the speed of the synchronous machine. So it is given by pi d ns. So your velocity va is equal to pi d ns. So the diameter of the machine should be chosen in such a manner, because see, we cannot exceed certain velocities, because the material has some strength to bear. If we go beyond certain velocities, what happens is that your material or your machine will break down. So that's the reason the diameter of the machine should be chosen in such a manner. The peripheral speed should not exceed 30 meter per second. Now this was about the elementary dimensions and the output equation. Now there are certain constraints while we are designing the stator. So in designing the stator, there are certain conditions, like how do we calculate number of stator conductors? This is one point. Number second point is the cross section of stator conductors. That is also important. The third point is the stator winding design. The fourth point is how do we calculate the number of stator slots. Fifth is your slot dimensions. Sixth is your depth of your stator core. So first we'll go for number of stator conductors. See, number of stator conductors, how you calculate is, see, when I was teaching you transformers in the class also, we have derived this equation. Let ES be the stator EMF per phase. So this stator EMF per phase is given in volts, and F be the frequency in hertz. This F you are seeing, F is the frequency in hertz. This phi m is the maximum flux per pole, and Ts is the number of stator turns per phase. And this kws is stator winding factor. So your stator emf per phase was is es is equal to 4.44 f phi m ts kws. The only difference here is you have this stator winding factor, whereas in the transformer it was not there. So number of stator turns per phase would be, now this ts would be es divided by 4.44 f phi max and your stator winding factor, that is kws. Now this ts is one turn. Yesterday in my, if you see, it is one turn, but one full conductor will have two turns. So if it is a single phase machine, for one turn it will have the number of conductors is equal to twice ts. So number of stator conductors per phase, that is for per phase it would be twice ts. Now in case it's a three phase machine, it would be 3 into 2 into ts. So 3 into 2 into ts would be 6 times ts. So number of conductors for three phase, it would be 3 into 2 into ts, that is your 6 times ts. So these are the number of conductors how you are going to calculate for a three phase machine. So for a three phase machine, if you calculate your ts, you have to now calculate the number of conductors. So you can aram say write zs is equal to 6 times ts. So now one more important and significant factor was how to identify the cross section of the stator conductors. So as usual, cross section of the stator conductors, in case of transformers also, we were taking your current density. Your current density is equal to your current divided by area. Similarly here also, see here what I have done, let as is equal to cross section of stator conductors in meter square. You have to see very carefully which dimensions you are having. If it is millimeter, centimeter, accordingly you have to substitute the equation. So this dimension and this unit is very important in calculation part. If you are being asked a problem, so it will play a very vital role, so you have to be very careful with it. So is is equal to stator current per phase in amperes they have mentioned, and here you see current density for stator winding ampere per millimeter square. So you know what to do, into multiplication of 10 power 6, and if it is centimeter square, then it is 10 power 4. So stator current per phase, because this is in meter, so we have to convert this millimeter square into meter only. If this is given in centimeter, then 10 power 4, millimeter, then this is 10 power 6. So you remember this, because it would be easy. That moment during the examination it will be difficult. So stator current I have also made you to write in the notebook, so you look at that also. Now stator current per phase. So see, current per phase would, your input kVA is in three phase machine, it would be 3 times your E stator into I stator. So it into 10 power minus 3. So your stator current per phase would be your input kVA into 10 power 3 divided by 3 into E phase, where here you see where ES is equal to stator EMF per phase. So cross sectional area is as will be given as IS, this is cross sectional area, AS would be given as current into your current density millimeter square. Now there are certain conditions with the different size and shapes of machine, so that is also very important. For example, in small machines, and the type of connection also, it is very important. Like you must be studying in your CAD class, drawing class, regarding the single layer winding and double layer winding, semi closed slot. So I will not go much into that discussion, but I will tell you what, like in small machine single layer winding with semi closed slots, are used, whereas for induction, the for large winding, whereas for induction and large machines, this means for small, there is some typing error over here. For large induction machines, double layer winding with open slots are used. That means for small machines, small induction machines, we are using single layer winding with semi closed slots, whereas in case of large machines we are using double layer winding with open slots. But usually larger winding is preferred. Why larger winding is preferred is as it causes decrease in copper loss and increases efficiency. Now see, if you are using a larger winding, what will happen is that your copper loss will decrease and your efficiency will increase. So usually your single layer winding is selected as per the given data. So single layer winding means it's a small machine. So rated power should be less than 10 kilowatt. Your rated voltage should be less than 600 volts, and your diameter of the machine should be less than 40 centimeters. Now these were the elementary, see, we were discussing in the very beginning. I told you first thing is number of stator conductors. So we came to know this number of stator conductors is Zs, and Zs is equal to 6 times Ts. So Ts we can calculate by substituting here in that formula. We can get Ts. Ts is equal to Es 4.44 F 5 max kWs. So these things would be mentioned. Now the second thing is cross section of the stator conductors. That means the area of cross section. That is current of the stator. Is by area would give you the current density. Usually current density is given, so you can calculate the area. So like here, you have calculated the area here. As is equal to Is by rho s millimeter square. So since I'm also sharing this once my class will finish, this PDF I'll be uploading. So don't worry, we are not able to take it down. And moreover, similar to this one YouTube video also I have uploaded. Those of you who have joined late can watch that also for your better understanding. Now the third point was about the stator winding, number of stator slots, slot dimensions, depth of stator core. So now we will be moving to the for this path, this point. See, number of stator slots. So means what? Number of stator slots. First of all, we have to understand how many number of slots are there in the stator, because stator is a stationary part. There are some slots in which windings are passed, so we have to understand the number of slots. Now for that, let's suppose SS is equal to number of stator slots, and your P is equal to number of poles, and your QS, which I have mentioned here, is equal to number of stator slots per pole per phase. Per pole would mean if this is a 4-pole machine, it would be 4. If this is a single phase machine, it would be 1. And if it is a 6-pole machine, it would be 6. If this is a 3-phase machine, it would be 3. So number of stator slots we are interested. So number of stator slots that form, see, D is equal to diameter of the stator. Now to understand how do we calculate the number of stator slots, see the number of states, this is 3 because of the 3-phase machine. It would number of stator slots would be equal to 3 times P, that is number of poles, into QS, that is number of stator slots per pole per phase. And also the number of stator slots, this stator slots depends upon what? It depends upon the circumference of the stator and the type of winding which we are employing. So this type of winding, for example, gamma SS I have written. So when this is gamma SS is when this is a single layer winding, so the difference between the slots would be 1 to 1.5 centimeter. Now when this is a double layer winding, then YSS would be equal to 1.5 to 2.5 centimeter. And usually your QS, that is QS, that is number of stator slots per pole per phase. See, it will be greater than or equal to 2. It cannot be less than or equal to 2. It will be always greater than and equal to 2. The reason behind it is that your see, the reason for number of stator slots, for example, this slots would be depending upon the type of the winding you are employing, the connection you are employing, the different lap winding, wave winding you are employing. So it would be around somewhere around this will come somewhere around 18 or 16 or 14. More than that it will come around 20, 24, 24. If you, for example, you suppose it's a four pole machine, four pole. Hello, please switch off. This is a four pole machine, and these are three phases. So you have to 24 divided by 3 into 2 is equal to 6. So this would be 4. So when we will be solving the problem, we will understand it in a much better way. Number of stator conductors. Now the total number of conductors which we are employing, it would depend upon your this zs by rho s. Now you have slot dimensions. Now what are the slot dimensions? Is flux density in the stator teeth. So this is VTS is equal to 1.3 to 1.7 Weber per meter square. This is a standard flux density which happens to be in the stator teeth. And minimum area of stator teeth per pole is phi max divided by BTS max. So this happens, BTS max is 1.7. So from equation 1 you got phi max by 1.7 is the minimum area of the stator. Again you can calculate this minimum area of the stator by its construction. Like you can have this your current density divided by number of poles into length, and this is the BTS, sorry, angular velocity which is minimum, and you can relate it, and you have this WTS minimum is equal to phi max 1.7 rho s p into Li. This is the minimum width of the stator teeth. So this is your width, and this is your current density, this is number of poles, and this is the length. What I'm much interested in here is, see, your stator slot pitch is equal to YSS is equal to WTS. That is your width. This width that you have calculated, minimum width, plus your WSS, that is there would be some dimensions. See, between the slots there would be some dimensions. This is equal to this. So depth of the stator slot normally is between 3 to 6. And see here, I was trying to explain you like this. You have, so this was your WSS, and then this is the DSS. So what is slot space factor? Is area occupied by the arc conductor in a slot divided by area of slot less than equal to 1. So these are some standard values which we are getting. Flux density in the stator core would be around 1.2 to 1.4 Weber per meter square. Your cross sectional area of the stator core would depend upon your phi. This is your flux, and this is your what, B is equal to your flux by area. So your cross sectional area would be equal to flux by BCS. Again, your cross sectional area of stator core is, cross sectional area would be again length into width. So length into width we can equate here, phi divided by BCS. That is because your area is equal to your B is equal to phi by A. So that, like that only I have written phi CS by BCS is equal to this. You can calculate from here. Now this you can understand easily. I have also solved one problem in my YouTube video also I have provided. And when you will be seeing reading it, so it is very easy to understand, because I have made this note very comprehensive. I'll be uploading it also. Now let's go to a problem and let's understand. We will be easily able to solve it, because the theoretical part was very dry. So let's move to the problem, and let's attack one problem. So I'll be reading out the problem. Please take your calculator also, if you are having, and pen. Write down this problem. I want you people to write down this problem, because it would be very good if we are going to solve this problem, and that way we can understand the concept in a much better way. So find the main dimensions. Find the main dimensions, number of turns. So you can see the problem states, find the main dimensions, number of turns, yeah, find the main dimensions, number of turns per phase. Here it is the problem. I'll be, yeah. So you read this problem first. Find the main dimensions, number of turns per phase, number of stator slots and conductors of a 15 kW 3 phase 2 pole 400 volt 50 hertz 2810 rpm squirrel cage induction motor having an efficiency of having an efficiency of 0.88 and a full load power factor of and a full load power factor of zero point 0.9. Assume specific magnetic loading is equal to zero point 0.5 Weber per meter square and your specific electrical loading, that is AC, which we calculated, is equal to 25,000 ampere conductors per meter. Take the rotor peripheral speed approximately as 20 meter per second. Use star delta starting. Now we have read the problem. So what is the thing is that whenever we are reading the problem, so you should hold the problem for 1 or 2 seconds or 5 to 10 seconds before just trying to attempt it. You have to really think inside your mind before inking on paper what how I'm going to approach it and what is it asking. So if you look at the problem, what it is asking is it is asking for finding the main dimensions. So what are the main dimensions? The main dimensions are length of the induction machine and your diameter. So that means it's asking for your D and L value. Okay, and it's also asking for number of turns per phase. So that means TS also it's asking. Now one more thing, it's asking number of stator slots and conductors. So it is also asking for your stator slots. So stator slots ZS would be equal to how much? 6 times TS, because it's a three-phase induction machine. It is given that it's a two-pole 400 volt. From here only from 400 volt also you can tell that it's a 350 hertz to having an efficiency of and a full load power factor. So we'll take down these values. And also one more thing is that assume kW, that is the winding factor, to be 0.955. So rating of the machine is how much? Rating of the machine is 15 kilowatt. So rating of the machine is 15 kilowatt, and your power factor of the machine is zero point 0.9, your voltage is 400 volts, your magnetic flux density happens to be 0.5 Weber per meter square, your speed 2810 rpm, your ampere conductors is 2500 amperes per meter, your efficiency is 0.88, and the velocity of the machine is 20 meter per second. So in order to get the main dimensions of the machine, yeah, so in order to solve this machine, how do we approach? So first of all, we know that we want the value of D square L. So we, from the earlier expressions also, we can write our C naught, this C naught D square L N. N is your what? N is your RPS, rotations per second, is equal to Q in kVA. Is equal to Q in kVA. Now here you can see your input kVA is equal to your output kVA by efficiency. Output kVA by efficiency. Your output kVA you can write as kW by cos phi. Kw by cos phi you can write. So your input kVA you can substitute this value, output kVA value, that is kW by cos phi into efficiency. Efficiency is there. So once you are substituting equation 2 in equation 1, you will get input kVA is equal to kW efficiency into cos phi. Same thing I have written, kW efficiency into cos phi is equal to your C naught D square ln. Now kW also, earlier also I have told, if it is given in HP, you can multiply, but here no need. Here we don't require because it's already given in kilowatts, it's not given in HP. This is if it is to convert, if it was 15 HP, if we had to convert it in kilowatt, then that case we had to multiply this with 0.746. Now we know the C naught is how much. C naught is your pi square 1.11. If you notice, if you multiply your pi square with 1.11, it will come almost around 10.96, something like that. So you can also safely assume it as 11. So this is 11 into 10 power minus 3, and here you have your kW value. So this kW value is given 0.955. Your average flux density is given as zero point 0.5. Your ampere conductors is given as 25,000. So once you are calculating the value of C naught, you get the value 131.3125. This was to explain you your cos phi is equal to that, because for that cos phi kW by kVA. So here you can just relate to this if you are not understanding how this has come. So inside I have written for your better understanding. Now the value of ns is 2f by p. Ns is 2f by p. F value it is given 50 poles, number of poles it's given 2. So f ns happens to be 50 rps. Now we can safely write your d square l is equal to your kw efficiency cos phi c naught ns. So kw is 15 kw, so this would be 15 into 10 power 3. So I have not written anything. Assume it as 15 kW or into 10 power 3. Here you have to multiply it either kW or 10 power 3. You write better. Efficiency it is given 0.88. Power factor it is given 0.9. And now your C naught we have calculated 131.3125. NS we calculated just now. This is 50. So once we are substituting all these values, only thing you have to be careful here, you have to multiply 10 power 3. So we will get around 2.86 in 10 power minus 3 meter cube, because this dimension is meter square and this dimension is meter. So this would be 2.86 meter cube. Now one more thing, if you go back to the problem here, you are looking. So your velocity, peripheral velocity, it is also given is 20 meter per second. This peripheral velocity is equal to how much? Pi dn, which we have seen in the beginning also, pi dn. So pi value we know, okay. Vs value we know, Vs value is 20, pi value we know, n value also here they have mentioned 2810. We can get the value of d na, you just see here. So now you can get the value. Peripheral speed is Vs is equal to pi d n by 60. Now why we had to divide it by 60? Because that value was given in rpm. N value is given in rpm, it is not given in rps. See here, that value, see, 2810 rotation per minute. If it was given in rps, no need to divide by 60, but this is given in rpm, so we have to divide there by 60. So that you have to be very careful. So here again we have to divide it by 60 and we have to divide it by 60. So we can substitute. Vs value is already mentioned. Vs value is given as 20, and we can 20 pi into d into 2810 divided by 60. From here you can calculate the value of d. Pi value we know 22 by 7 or 3.144. So the d value you get, d value is 0.136 meter. Now you already had your d square l value. You had d square l value, you just now sort, it is 2.86 in 10 power minus 3. Now you calculated the value of d, and the value of d is 0.136. So you can easily multiply this d square l, and you can get the value of l. So your d square, this d square divided by 2.8 in 10 power minus 3 will give you the value of l. So 0.151 meter. So now we have got the main dimensions d and l. We have arrived at the main dimensions. Now let's look at the problem one more time. And what is the problem asking us? So So find the main dimensions. So we are done with the main dimensions. We have calculated the value of D and L. Now another thing is the number of turns per phase. So number of turns per phase means it is asking for T phase. That is your T phase. Number of stator slots and conductors. See, number of stator slots and conductors would mean it is asking us for stator slots means 6 times, because your total, so sorry, your conductor means your conductor forms 2 turns. 2 turns is equal to one conductor. So your ZS is equal to twice for a single for three phase it would be 3 into 2. So it would be 6 turns. So first of all, let's go for the number of turns which it is asking. So now we have calculated D and L. So turns per phase we know. Turns per phase we know it is your V phase divided by 4.44. This is the stator winding factor, your frequency, and your flux. So flux here, we have seen your flux per pole. Is it mentioned over there, flux per pole? The value of flux, let's see in the given. See, nowhere the flux per pole is mentioned, nowhere it is mentioned. But do we have any relationship from these equations or quantities? Can we calculate the average flux? Yes, we can calculate the average flux, just like in the transformer when you used to have these things. Flux was equal to what? Flux is basically your average flux density, means your flux by area. BAV would mean your flux by area. Now this is given. So can you calculate? Yes, we can calculate. And your area, see here, uh, your see, this is your flux per pole. That would depend upon your average flux density. That is your pi dl. Pi dl BAV divided by P. So what is this pi dl by P? We have seen pi dl by pi d by P. Pi dl by P is your, see, this is your flux per pole, which we have also established in your output equation. Please go to the previous section and you just can also watch my video for this particular derivation. So we can substitute these values here. Pi BAV, D value we have calculated, L value we have calculated, number of poles he has given 2, and we can substitute here. So your flux per pole, see, this is not your flux, I mean, if you want your flux it would be this much only, pi BAV DL, but because it is per pole, hence P has come over there. So it would be around 0.0161 Weber. Now stator turns per phase you can calculate aram se. This is TS is equal to V phase 4.44, KWF 5M, KW value you have 0.955, F value you have, it is 50, 5M value you just now calculated 0.0161 Weber. So you have this 400 is equal to 4.44 divided by 0.955 into 50 into this value. So you get the value of number of turns. So it happens to be 117. Now one more thing it is asking is that number of stator slots. Now let us assume that slots per pole per phase M is equal to 3. So slots per total, so total number of stator slots would be equal to, see, he has assumed, why he has assumed this M is equal to number of stator slots. Let us assume that slots per pole per phase so is equal to 3. So that would mean, because it should not be less than or equal to 2, earlier only I have mentioned, and we cannot take this as an integer or any value. So sorry, we cannot take this as a decimal value. You have to take the next integer. That means if 2, the next integer to 2 is that without decimal figure, that is 3. Hence we have taken this as 3. So the total number of stator slots accordingly would be slots into number of poles to phase. It is a 3-phase machine, so it happens to be 18. It happens to be 18. Now total number of conductors, already I have told, total number of conductors means Z, is Z. So Z will form one conductor is 2 TS and 3 phase, so it will be 6 times TS. So 6 into 117, it happens to be 702 conductors they are using. Now number of conductors per slot, number of conductors per total number of conductors is 702 and number of stator slots is 18. So number of conductors per slot is 702 divided by 18 is 39. So we have arrived all the values we calculated, whatever was asked we have calculated. We have calculated the diameter, we have calculated the length, we have calculated the turns per phase. Now this also we have calculated the total. This is 18, not 118, so please be careful, there is some typing error here. This is 18 and this is the number of conductors, total number of conductors, this is 702. So this was my lecture. You have any doubt in this or any part? Can any one of you, if you have any doubt, you can ask me, please. Hello, hello, anyone is there?
No doubt, sir.
Yes,
Yeah.
sir.
Yeah, where you tell me. Yeah, I'll go back. You tell me where you are having doubt.
No doubt, sir.
Huh? Okay. Now, if you're see, I'll be okay. I'll be presenting one more time. This we will do some revision to this. Okay. Where is it? Wait. Mm, Wait. Mm, huh. So I'll be revising it. So how we have arrived at this is, first of all, what we have done. So these are basically, we are going to calculate the dimensions of induction machine. So the main dimension of induction machine is the diameter and the length. So d square L. So where we have seen the output equation also we have calculated, and the output equation formula, that is the earlier formula which we have derived in the previous class, was around kVA is equal to C naught d square LNS, wherein your C naught was equal to 1.11 pi square, your average magnetic loading, or BAV, this is also called as specific magnetic loading, into your electrical loading, that is your ampere turns per conductor AC, into your winding factor kW into 10 power minus 3, which we have seen. This your C naught was equal to this. And one more important thing is that your kVA, if you have to write your kVA would be equal to your kW divided by efficiency into cos phi, that in the problem section also we have seen. So now the thing is that how do we substitute other values like this? How do we take the core your length and your core pitch value? So there are certain conditions for this. So ratio of core length to core pitch should be, your core pitch is your pi d by p. So there also you have seen, when we are calculating the pitch or this, so this is your pi d is your basically circumference. So your circumference of a circle is 2 pi r. So your 2r is equal to d. So instead of writing 2 pi r, we are writing it as pi d by p. So your L by Z ratio, if it is not given in the problem, if it is given, usually we will take L by Z is equal to 1. Now if it is written as for best power factor, so we will assume Z is equal to under root of 0.18 L. Now for a minimum cost, you will take L by Z is equal to 1.5 to 2, and the distance covered by the machine, that is your peripheral speed, that is given by pi dn. Now for example, your n value is in rpm. In that case, for example, it is given 3000 rpm. In that case, your VA would not be pi dn, it would be pi dn by 60, because you have to express that in case of RPS. See here, please note here, ns is equal to synchronous speed in rotation per second. That's why I have written VA is equal to pi dns. Now for example, this ns is given in minutes, so we have to surely divide this term by 60, as in our problem we had to divide it by 60. So usually the diameter of the machine should be chosen in such a manner the peripheral speed should not exceed 30 meter per second. Now there are certain things like the design of the stator. In this problem we have not taken too much into the design of the stator, but one problem I have put on YouTube. I'll be sending you the link also, you can copy also the link. Therein you can see these factors also I have taken into consideration. This problem which I have solved, similar to this problem, has appeared in VTU examination, and that problem constantly, that which in YouTube I have uploaded, is I saw 2 3 problems repeatedly like that coming in the examination, so you can have a look at that also. With this basics you can understand it very easily. So this is for the design of stator. You have certain criterias. So number of stator conductors, in this case cross section of stator conductors, stator winding, number of stator slots, how you are slot dimension, depth of stator core. So number of stator conductors you already know. You have to calculate the value of TS. Here you can see, you calculate the value of this is your number of stator turns per phase. So your one conductor would be equal to your two turns. So your ZS would be equal to 2 times TS. So here you can calculate, just in the case of your transformer also we were calculating your number of turns. In a similar fashion you can calculate here also. Now if you have to calculate Z would be equal to 2 times TS. In case of a three phase it would be multiplied by 3, so it becomes 6 TS. Similarly, your cross sectional area of stator conductors, see, let AS, if so you have to calculate the value of AS. So you know that your current density is equal to your current by area. So the AS would be equal to current by current density. So you can calculate the value of current from here, and you can back substitute here. You can write AS is equal to IS by this current density. Now there are certain conditions. For example, in small machines we use semi-closed and single layer winding. In larger machines we use open-ended winding, and double layer winding is used. So single layer winding is preferably used for a machine which has a rated power less than 10 kilowatt and rated voltage less than 600 volts, and the diameter of the machine is less than 400 centimeters. Now, how do we calculate this number of slots? See, here I have mentioned QS is number of stator slots per pole per phase. So this QS cannot be equal to less than equal to 2. It would be always greater than 2. Usually we will take this as 3. So in my another problem which I have solved, please have a look at it. So how I have calculated, it will be very it will clear your confusion in that regard. So this is the number of stator slots. So how you calculate is this formula and your current density, and this is the range. For example, yeah, hello, any
Sir,
doubt?
we have DSP class at 4 o'clock, sir.
Okay,
So
okay,
can you take up?
okay. So I'm winding up my class right now. So what we'll do is that I'll take the attendance. I'm putting this in my what I say is that I'm putting this in my Google Classroom. One more important thing is that, wait 1 second. One more important thing for me is you have to, yeah, is this, no, wait. One important thing I have. So wait. Hmm, wait. Uh, this you can note down. I have uploaded one video wherein I'm taking the stator slots also into consideration, and that has appeared repeatedly in the VTU examination over past 5 years or 6 years, I'm seeing this problem is coming for 12 marks, 10 marks, like that. It is coming repeatedly. So please practice this and see to this problem, and one or two problems like this I'm going to give you as an assignment also. So please look at this, and I'm stopping my class. So all of you have entered the attendance. Hello.
Yes, sir.
Yes, sir.
Okay, now I'm seeing only 22 are there present. 23. What happened? Only 23 people are there right now. I'm only taking this 23 attendances.
No, sir, somebody left, sir. Just 5 minutes back, somebody left.
So,
They have
so,
network issues, sir. They have network issues, sir. They
Oh,
left, sir.
okay. Wait 1 minute. I have to. Yeah. Okay, we will. Wait. 1 second. We will end the class here. Wait. Okay. Thank you very much. I'll end the class.
Thank you, sir.
I'll end the recording. Wait 1 second. And this. Yeah.
What about attendance, sir?
The attendance I've taken from the chat.
Yeah, okay, sir.
Okay. Attendance I've taken.
Thank you, sir.
Thank you very much. Yeah. Thank you.
Thank you, sir.
Thank you, sir.
Yeah. Thank you very much.
Lunch, sir.